Hello everyone, welcome back. Today we're going to talk about this device called the U-tube manometer. So let's begin with just beginning to imagine you have a glass tube that is shaped of a U as drawn over here. So if you put liquid into the tube, right, what is going to happen? It's going to find its own balance, right? And since both sides are exposed to the same atmospheric pressure, your liquid is going to be at the same level of height, correct? Because same level will have the same pressure. Okay, and what if now you take this U shape, right, and chuck it to a point and connect it to a point of a pressure vessel, sort of a vessel with a different pressure? What's going to happen if the pressure inside the vessel is found to be higher than the atmospheric pressure, meaning that the left side is going to exert a higher force compared to the right side, right? And then you will see that these two liquid levels are going to shift. Because of the push, the right side is going to go up and the left side is going to go down. Okay, so that's what happens when you insert a U-tube manometer in this way. Imagine your vessel is actually a water pipe flow, right? Across this channel over here, this pipe over here, and what you want to know is the pressure at the middle of the pipe here. So what you do is you take this U-tube manometer and insert it right at this level, okay? And because of the pressure inside, it's going to push the liquid level over here, and this we call it the measuring fluid, and usually is a very heavy, a very dense fluid, and we sometimes and often use mercury. Okay, so what's going to happen is that the pressure at A is going to push this mercury up, and there is going to be a difference in height. Okay, the thing is, how do you then measure the temperature difference? Okay, you use the liquid column units, which we have learned previously, which is rho g h. Okay, let's see how you do this. First of all, you have to take two points at the same height within the same liquid, and the typical 2 points that we take is here and here. So these 2 points will have the same pressure. Okay, within the same liquid, the 2 points at the same height will have the same pressure. So let's say this is 0.1 and this is 0.2, and you can say that P1 is then equals to P2. Okay, and what is P1 over here? P1 over here, right, is actually, if you imagine the stacking effect, so PA is going to exert pressure here together with the pressure caused by this column of liquid here. Okay, if this is water, okay, and we call this H1 now, okay, and so P1, right, is going to be PA plus rho G H1. Okay, so here you can write PA plus rho of water G H1. So this is the pressure at 1, this plus this. Okay, how about the pressure at the right hand side? Right hand side, you have what? You have atmospheric pressure, okay, and the contribution by this extra column, this increased column of mercury. So we have P atmosphere plus rho of mercury G. Okay, so this height we can call this H2, right? So rho G H2, and from here, right, because you can visually measure H1 and H2, and you have the density of mercury and water, you have the value of atmospheric pressure, you will be able to find PA. Okay.